Okay, good morning to all of you. So even though I defined these definitions earlier, but I will go through quickly so that before other people join, we will also revise and they will also not lose much. So you know that input alphabet alpha output alphabet is FQ, finite field FQ in this course. The message U is a block of symbols that is actually from FQ power K. Encoder is a map from FQ power K to FQ power N, right? So image C is exactly the image of C means code. Code is exactly the image of this function, encoder function. That means it takes element from FQ power K and map it to FQ power M, right? So the domain is entire FQ power K. And since it is a function, so every element has an image. So all FQ power vectors are inputs, okay? And what are the images? They are the generally this function FQ power encoder function is a 1-1 function. So the cardinality of C is the cardinality of FQ power K, right? But if FQ power K is a linear space, if C is a linear code, then the dimension is exactly Q power K, correct? K is the basis dimension of the vector space FQ power K. The block length is n and the dimension is k, and the rate is defined as k by n, and received vector the received vector r, right? um, One minute. Yeah, so the received vector r, the output of the channel is possibly corrupted version of the code word C, correct? Yeah, right. Okay, so the decoder is a map which decodes, means which again converts FQ received word to the original message, right? Okay, good. So then this is the little new stuff, but same we discussed, but I wrote so that it will revise things. When you are having a conversation with a friend over a cell phone, right? Your voice is turned into digital data, and the error of correcting code applied before received to friend. When our friend receives the data, the errors in the transmission must be accounted for by decoding error correcting code. Only after decoding the data, the error in transmission, only after decoding the data turned into sound that represents your noise, right? So the amount of delay it takes for a packet of data to be decoded is critical, okay, in such an application. So if you took the several seconds, then delay would become aggravating and make holding the conversation difficult. The problem of efficiency of decoding code is therefore critical importance. In order to decode quickly, it is helpful to have some structure to the code rather than taking the code random code, okay, a random subset of a power n. That's why we will take the linear code. The reason for taking linear code is that one. So NMD code C over FQ is a linear code. You know it is a subspace, right? So subspace, you know the definition. So yeah, redundancy bits and all, you know. So in the linear code now, okay, in the linear code, the distance of the code is defined as distance of the code is equal to the minimum of the distances of all code words, different code words, C1 not equal to C2. But that is same as weight of C1 minus C2, right? But now since C1 is not equal to C2, C1 minus C2 is not equal to 0. So this can be converted into minimum of weight of C. C belong to C minus 0. This I am using throughout. Okay. This is the one I am using throughout. Okay. Encoding linear codes and yeah. So this I already explained. In the linear code, especially this encoder is by there is a generator matrix. Yeah. And generator matrix, if it is, we can easily convert it into by equivalent code. We can convert it into systematic form, right? That is IA, where I is a k cross k matrix and the k is a k cross n minus 1 matrix, right? Yeah, these things you are aware. Now I'm starting actually today's lecture. Let C be a linear NKD code over FQ. The parity check matrix for C is a R cross N matrix, right? In fact, R is N minus K. That also you know over FQ, such that every code word C belong to C, right? Every code word is a satisfy this property H into C transpose is equal to 0. In other words, the code is right kernel of H, means kernel of H, right? And so you know the relationship. So rank of H equal to n minus the kernel of H, so it is n minus k. So that R value is that. Okay. Yeah. I'm just you know these things, but again I'm giving the proofs for these small things. Let G be a k cross and generator matrix C. The rows of G spans kernel of H, right? Hmm. Hence, in particular, G into H transpose is equal to 0 or H into G transpose is equal to 0. Hence, the dimension of the kernel is equal to n minus rank of G, right? N minus k. Yeah, hence the rows of H spans kernel of G. So the parity check matrix of the linear code can be computed finding the basis of the kernel of the generator matrix of the code. Okay, so this we done in the previous class. So if G is the generator matrix in systematic form, then H can be evaluated minus A transpose into A. By multiplying it, we can check easily, right? The interesting point is that so, for example, C is a code word in C with Hamming weight t greater than 0. What is the meaning of that? So listen this carefully. So let J contained in 1 to n such that the support of C, that is J is a set of indices of the t non-zero entries of C. Right? Are you following this? Okay, I'll explain you. See, C1, C2, Cn is a code word, right? But C1, C2, Cn has some weight. What is the weight? You know, non-zero elements. Weight equal to t, right? So once weight equal to t, then what happens? Out of the C1, C2, Cn, only t coordinates are non-zero, right? Now I'm calling wherever it is non-zero, that is called support of that code word C. So that is J, right? Now, when you take it, this H into C transpose is equal to 0, then the remaining, so actually H into C transpose, what it is doing? It is a linear combination of the columns of H, right? So this is equal to 0, right? But already certain, for example, C1 may be 0, right? C1 is not in J. So like that, they are already 0. So some of them are left. Now it is a non-zero linear combination of the columns of H. So that means those particular columns now become linearly dependent. Is it okay? Anyone of you? Any doubts? Is it fine? Yesterday also I'm
Yes, sir.
trying, somewhere I made a mistake, so that's why some typo may be there, that's why it happened like that. Okay, I'm repeating. H is a parity check matrix. So these are columns. H1 is the first column, H2 second column, like that, right? Okay, you know that how many rows will be, columns are n only, correct? How many rows will be there? We have n minus k rows. Okay, now you took a, now this is a code word. Code word has a weight, some weight t. So I take a j where these are non-zero, right? So then what is happens? H into C transpose will tell you that this linear combination of the columns equal to 0. But these are non-zero now because they are in J. So the Cj is non-zero. Okay, for each J in J, right? Because of that, these particular columns becomes linearly dependent. So what is happening is that, so the so so linearly dependent columns and a code word with weight are linked. Okay. Conversely, every t linearly independent columns defines a at least one non-zero code word C. Okay. That's why this is the main thing. Let HPA parity check matrix of a code, okay, non-zero, then the minimum distance C is the largest D such that every D minus one columns in H are linearly independent. If there are dependent, then I have a code word with that weight. Very simple, but very powerful. Yeah. So that's why I wrote in a pink some color. Okay. The minimum distance of the code is the D. In fact, it is if and only if condition. So D minus one columns of which are linearly. So, and also this is the largest D. What is the meaning of that? It's largest D. Every set of D minus one columns. Understand? If there is a set of there is at least one set of D columns which are linearly dependent, then I have a code word with that weight. So if I take any D minus one columns, that is linearly dependent, but there is a D, there are D columns, they are linearly dependent, right? Yesterday you saw the one matrix, right? There you checked that a single columns, all single columns are linearly independent. Any two columns also linearly independent. That means that is why I wrote code is greater than 2, but there are three columns which are linearly dependent. Now suddenly when we have three columns which are linearly dependent, then the code is less than or equal to 3 now. So it is exactly equal to 3 later, right? So this is we'll use today. These are all previous things only till now whatever discussed. Now today I'm going to discuss a new concept that is called syndrome decoding. Okay, what is syndrome decoding? But syndrome decoding is used for linear codes. Let R be a received word, then how R look like? V plus C, where C is a code word and V is a coset leader. You remember this yesterday? Any questions? I can explain otherwise. You remember yesterday table? We make a standard array. You remember that? Amya, are you clear?
Yes, sir.
Mahek,
Yes, sir.
yesterday you remember that I made a standard array. That first row is code words and the remaining are cosets, right? So if I take a received word, then it is in the table, somewhere in the table. When it is in the table, that is equal to V plus C, where V is the coset leader, right? If already there is no change, all R is itself is a code word, then what is V? If R is already code word, then what is V?
Zero.
Zero
Zero.
vector. Yeah, zero vector. So right. So if R is a code word, then V is a zero vector. That I already written here, but now observe that V into H transpose is equal to V plus C into H transpose. Right. Yesterday I mentioned it. So V into H transpose plus C into H transpose. I explained with one example yesterday. But C into H transpose is 0. So it is V into H transpose. Right. So it is sufficient to compute the this part. So that we defined as a syndrome of a vector R. Denoted as S of R, it is defined as S of R equal to R into H transpose, or you can also transpose this, it's not a problem. If you put like this, then it is a row vector. If you transpose it to a column vector, but that does not take much importance to that. Okay, so I will explain you what actually happening. So for a given linear NKD code C with a parity check matrix H, these are all given. Code is given, parity check matrix also given. Then the syndrome function S is a map from where to where, fq power n to fq power n minus k. Okay, defined as S of V equal to HV transpose. Okay, I told you already, do not worry much about R into H transpose or H into R transpose. There it is a row vector, here it is a column vector. But this is familiar to you, that's why I wrote in the box now. From childhood, you are reading like this, so that's why I put this way. Note that rank of H is n minus k, and null space of S is the code C. So, and the range space is fq power n minus k for S scaling, because rank is n minus k, right? Rank is n minus k. So range space is also fq power n minus k. That means it is an onto function. Okay, it is an onto function. Further, that also I will write here. Further, as partition the domain fq power n into equivalence classes. The equivalence classes are exactly the cosets of C. If you choose the coset leaders as representatives of these equivalence classes, as they have the smallest weight within the coset, right? The received word are corrected to code word R minus C, where E is the coset leader of the coset where R belongs to. Is it okay? Yesterday I explained through example, but today I wrote everything in it clearly. So if you have a problem, then I can explain. But before that, I will do one thing. Okay. What I will do, I will ask some questions here. Yeah, any questions? By the way, do you have any questions? Okay, I made a mistake. I will open it in a other form. Otherwise, I cannot write it. 1 minute. Pausing the recording. Okay. So let me share the screen again. So okay. So this is the this is what I'm saying. So for example, you know these things, right? So let us see recall something you already aware of. For example, you have a function, right? I'm telling very basic things now. So this part you already know. Okay. So let f is a function from A to B, right? F is a function from A to B. Then you know that every element in A has an image in B, right? So now I take a small b. So B belongs to B, right? So I'm defining some set. It is not inverse map, okay? Please remember, it is not F inverse. F inverse may not exist, okay? F inverse of B is defined. How it is defined? Do you know? Somebody help me. What is F inverse of B?
The set of all A in A such that f of A is equal to B.
Yeah, set of A in A such that F of A is equal to B. It is exactly the pre-images, right? So I have B here, I have A here, right? So there are many elements are mapped to single vector B, correct? So this is my B, right? There are many are mapped to B, right? So many are mapped to B. So I'm collecting all those, right? So that is the set. Okay. Now with this thing in hand, so for example, x comma y belong to A. I am telling that x is related to y if f of x equal to f of y. Since f is a function, f of x is an element in B, f of y is an element in B, and for every x and y there is an image. But I am telling they are related. I am defining a relation. I am saying x is related to y if their images are equal. Okay. I am asking a question. Is it an equivalence relation? Check one after the another. Is it reflexive? Is it symmetric? Is it a transitive? Because equal to is not a problem, right? F of x equal to f of x, so reflexive. F of x equal to f of x and f of y equal to f of x. Y is related to x is related to y, f of x equal to f of y is related to z, f of y equal to f of z. So f of x equal to f of z, so x is related to z. So it is transitive. It is an equivalence relation. On which set? Equivalence relation on which set?
A.
On A. So equivalence relation, what it will do? It partition the set. What are the partitions we'll get? Exactly this, right? How we can write A now? Is it why it is partitioning? So can two yeah. So my intention to say that so F inverse B1 and F inverse B2, F inverse B1 and intersection F inverse B2. What is this set? F inverse B1 is a subset of A. F inverse B2 is subset of A, right? So it is subset. That part is okay. What is this set? Can somebody help me?
If B1 is not related to B2, then it is empty. If
Otherwise,
B1 is related to B2, then they are
not required. See, it is always empty. Only thing is that B1 not equal to B2. I am taking that. Okay. B1 is not equal to B2. Otherwise, nothing, right? Intersection becomes same only, na? At least I am assuming this, okay? Now,
okay.
can you
Then
tell
it's
me
empty.
why it
Then
is
it's
empty?
empty.
Yeah? Yeah.
Because equivalence classes are disjoint.
No, not that unnecessarily you are going. See, what is the meaning of x belong to this?
Then the function does not become well defined.
Function, it is not a function first, okay? X belong to f of b1 intersection f of b2, f of x equal to b1 and f of x equal to b2. So single element has two images. That is not a definition of function. It is a function. So with respect to of equivalence class and all, forget about that. It is always empty, right? So that is one thing. And luckily here it has a if it is onto, then every element has a pre-image. That's okay. But finally, what is that happening? Now I can write A equal to union B belong to B, F inverse of B. Are you following this part?
Yes, sir.
Yeah, good. And it partitions A, and their equivalence and their intersection is empty, and it is equal to A. So F inverse B is empty when F inverse B
A
is empty.
is not in the image.
That means no, not like that. F inverse B is empty. That B is not in the image. B only you are told. B is not in the image of F, right? So empty also not a problem, but if F is onto, then these are all non-empty and their union equal to A, right? That is exactly happening in the syndrome function also. That is what I want to convey. But one more advantage, see, this is everywhere, okay? You know now F is a map from group G1, group G1 to group G2, or vector spaces, or rings, or whatever, right? And it is a homomorphism. It is homomorphism, right? Uh, then what is going to happen? Can you tell me now what are the F inverse of B and all? If it is a homomorphism, what is F inverse of 0? It is not only function. I told it is a homomorphism now. Every homomorphism is a function, but function is not homomorphism. But I know that the sets have structure G1 and G2, and the function also has structure. It is a homomorphism. Then how the this equivalence classes look like, right?
F
Do not.
inverse 0 will be kernel of
Yes, please.
A. Kernel of F.
0. The, no, what is kernel of F? I am not following.
F inverse 0 will be kernel of F.
F inverse 0 is kernel of F. F inverse here you take identity E2. So uska inverse is kernel. But what about if I take arbitrary A? B of element. What is F inverse of B? Right? So the beauty is that if it is a homomorphism, one element, identity element ka inverse image is kernel. And not only that, if you take any other element whose inverse is exactly kernel plus that, it is a cosets. Right? This is a beautiful part. Generally, particular faculty may not ask you those questions. What is that I want to say is now, see, here three elements are mapped to this, but only one element is mapped to this, right? That means that these equivalence classes need not be of same size. This F inverse B need not be of same size. F inverse B cardinality equal to the how many elements are here, right? They need not be of same size. But F is a homomorphism, then all equivalence classes are of same size. That is equal to the size of the kernel, right? Kernel is a normal subgroup. So all cosets. So they are exactly the cosets. That is what I want to convey here, right? I'm not doing any high mathematics. Okay, all you done only I'm doing. Okay. Any questions? So now syndrome is what? Syndrome is a linear transformation. Right? Syndrome is a linear transformation. Linear transformation from where to where? Do you recall? Just a few minutes before I told. Syndrome is a map from where to where? Fq power n to Fq power n minus k. And it is surjective. And what is the kernel of 0? What is the preimage of 0 map? That is the code C. Right? Again coming to that. So, and the representatives are the coset leaders, right? Okay. So that is all these theorems and all, right? I told everything very beautifully. So now these results becomes easy. Two vectors belong to the same coset if and only if they have same syndrome, right? Yeah. So that is very simple. And so what is the final thing now? Now we construct only the syndrome lookup table. Earlier we have a standard array. In the standard array we put all the elements of fq power n, right? You remember each row contains fq power k elements, and there are fq power k, fq power k, fq power k. How many will be there? How many rows will be there? That question also asked. It is q power n minus k, right? So q power n minus k vectors will be there, but each of them, each row will give same value syndrome. That means how many different syndromes will be there? They are all distinct also. Total how many syndromes are there? Q power n minus k syndromes, right? So now I need to compute only the syndrome table only. That is called syndrome table. Okay, how it is done? How we can use it to decode now? So for a received vector R, calculates a syndrome R into H power T. But that is only same as now next the find the coset leader for the same syndrome S of R, right? The coset leader is C0. Then decode R as R minus C0. I think I also wrote here, right? Then the received word R can be corrected to code word R minus C, where he is the coset leader. Right? Any questions? It is because I am not showing yesterday's examples. Are you remembered those? Is it okay or not okay? Achila, are you remember those?
Yes, sir.
Achila Mahek. Okay. Now I am explaining this now. For example, you have a code, okay? So the syndrome table is given like this. Look at I'm explaining here. 0, 0. This is the first row in the standard array. What is the second row? Do you recall? What is the distance of this code? Now a little fast. Even
Two.
it is 2. They are not even, but the distance is 2, right? Distance is 2, then automatically, uh, so they does not contain weight one vector here. So I'll take 100 is the first coset leader, right? Now I will add 100 to all of them. Then I'll get that row, but I'm not worrying about them now, right? So I'm just computing the syndrome for this. But what is the matrix now? What is H now? H is this, right? You know how to get H, right? What is G? Can somebody tell me what is G in this example? 1011 01 10. I'm taking these two code words, right? So their sum is equal to uh, um, yeah, their sum is equal to this, correct? So yeah, so this is the generator matrix. What is the H now? You take uh, so this is H transpose, but what is H? H, what do you compute? So you take this as a column, right? 1 1, and you take this as a column 1 0, and this you write 1 0 0 1, correct? Now the first column is this is H transpose, okay? This H transpose. I am multiplying like this. If you want, you can multiply H into this also, okay? Now you can multiply here 0 1 0 1, right? Okay. Anything is okay. In that case, we're going to get like this. See 1 1 1 0. 1 into 0, 1 into 1, 1 into 0, 0 into 1, so I'll get 1. Right? 1 into 0, 0 into 1, 0 into 0, 1 into 1, 1, right? We got this. But 1 1 is what? 1 1 is what? 1 1 is where? Here. Right? Now I subtract this coset leader from here. Right? Then what I am going to get? If I subtract, so I'll write here 1, 0, 0 0, but subtracting is same as adding in the binary, right? So this is 0, so this is 1, so this is 1 1 0 1. Is it a number here? Yes, is correct, right? So that way I corrected this received word. This is not a code word, but I corrected decoded to this 110. Is any question? Are there any questions?
Yes.
No questions, everything fine? Good. One more example if you are not clear. So for example, I have a binary linear binary 633 code is given like this. Okay. Yeah. So now then the parity check matrix H is given like this. You know, the coset leaders are the and the syndromes are given like this. Okay. Are you fine with this? Oh, see, the first coset leader I took like this. Don't worry, whatever you take. Yeah. So coset leader is 0 0 0. When it is all 0 vector, syndrome is also 0. So we have all, look at here. We have all vectors. We have all possible vectors you get here. F power 3 n minus k. We'll get all the vectors, all possible vectors. Right? So how many vector syndrome is a map, right? Syndrome, and now S of V is equal to, according to here, it is VH transpose. Okay. What is the pre-image of 0 0 0? Which vectors will map to 0 0 0? All code words, right? We don't know whether we are following or not, but
Yes.
yeah, okay. So these are the pre-images. These are the images of the entire coset. Entire coset corresponding to this, all the entire row mapped to this. Okay, that is the beauty of linear codes. Now, instead of constructing that big table, yesterday standard array, I am now constructing the syndrome table. Right? Yes. Now we can correct things. So for example, I received this. Okay. So this it is not a received word, maybe code word. Then I will compute 101. So 101 where it is. So this one, right? 101 is here. Now I look at the coset ladder. Now I will subtract that. And this is a now a code word. So I'm corrected that the code. So can I proceed? I have any questions? Is it everything fine till now? You need more examples or it's okay? Okay, so then I'll proceed. So today my topic now this is the last topic. Now it takes time. So these are bounds actually, bounds on codes. Okay, please ask questions. I'm going a little slow. We done this also yesterday, but at that moment I'm not mentioning things clearly. So I'm bringing now. So first bound is singleton bound. What is a singleton bound, right? Okay, let CBA and NMDQ code. See, I'm not saying it is a linear code. If it is a linear code, generally we'll write like this: N, K, D, right? Where K is not the size of the C, its size becomes now Q power K, right? M becomes Q power K. Yeah. Okay, so these bounds are for any codes, including linear codes. The distance between any two code words is greater than or equal to D minus 1, correct? Okay. Right? What is I am doing now? If distance is D means distance between any two code words is greater than D minus 1, right? I'm defining a mapping now. Where to where? FQ power n to FQ power n minus D minus 1. How I map it? So I took n vector, n length vector. So A1, A2, AD minus 1, first D minus 1 vectors, and AD plus 1, AN. Okay. So where it is mapped to? AD plus 1, AN. Is the map is clear? Nothing is there, right? This map is not a problem, I hope. It is just simply I'm truncating the first D minus 1 values, puncturing I'm removing these coordinates, right? Now can you say me that what we can say about this vector now? I'll get how many vectors I'll get? Many vectors I'll get. Okay. If I take two vectors of this form, images, what we can say about them? If I take two code words, right? So code word C1 is giving one vector, right? So I say AD plus 1, right? And so on, AN. C2 another code word, okay? That is B1, B2, BD minus 1 like that. It will map it to BD minus 1 and so on. So is it possible that they can be equal? That is a question. Is the question clear? Here I have to use the D is the distance and all that stuff. Yeah, can you suggest me? Or they can be equal? Achila? No problem. Tell me that you are not clear or something. Mehet? Say something, no problem. If I am unable to tell, I am not clear. Say something. Okay, no problem. What I can do. So then Amia, you comment any?
So they can be equal. I mean,
They
so
can
if
be.
the last n minus d plus 1 coordinates are equal in C1, C2, then of course the image will be equal.
What happens if the last D plus 1 coordinates are equal, right?
Then
If these are
only
all
the first d minus 1 coordinates will contribute to the distance.
No, no, if these are all equal, right? Now first d minus 1 only will contribute to the distance,
Yes, sir.
but distance is d.
So
Huh? See,
so
yeah, these two are equal like that for everyone. So at least I can find two code words, right? At least I can find two code words. These two are, in fact, no, none of them are equal. See, if they are equal, right? Suppose they are equal, then what we can say about C1 minus C2? Can you tell me?
the last d minus n plus 1 coordinates will be 0.
These are all zero, right? How many can be at most non-zero now?
D minus 1.
D minus 1. Then what can be the weight of this code word? This is also code word, right?
It cannot be d minus 1 because the minimum is d.
Uh,
So it has to be 0.
yeah, distance actually. Sorry, no, I do not take weight actually. So I should not take weight actually. In the linear case only this will work. But okay, sorry for that. So sorry. C1 minus C2, it is for any code, right? So what is that? My point is that still they have distance one, right? Are you following that point?
It's to what is distance 1?
At least they have distance one. Total distance is d, right? What is that I want to say? See, so I take the vector, right? So I'm truncating the first d minus one values, but distance is d. If, for example, if they are equal, then distance becomes zero, right? And here, distance between these two become d minus one at most.
No, but that can happen if C1 is equal to C2.
Yeah, I'm not taking C1 equal to C2. Yeah, anyhow, that I'm okay. Yeah, so C1 is not equal to C2. Okay, I am assuming that to this part. Otherwise, of course, I cannot. Yeah, C1 is not equal to C2, then these are also not equal. That means that this map is 1-1 map, right? This is 1-1. This is one approach to prove. I will prove in various ways, singleton bound. Okay, so then this phi of C1 equal to phi of C2, C1 equal to C2. That is what I'm saying, right? So this is 1-1 map. If it is 1-1 map, um, uh, yeah, it is 1-1 map on C. Try to understand. Restricted to domain C, right? Then what is the size of M now? Size of M equal to cardinality of M. That is, but we have the cardinality of C is less than or equal to q power n minus d minus 1. Is it okay?
Yes, sir.
This because this is now 1-1 map means the C sits inside f q power d minus 1. So cardinality of C is less than or equal to this, right? So what is that I want to say? If you have this code, then m value is at most q power n minus d minus 1. We cannot have more than that. Okay, so it depends upon once n and d are given, what is the maximum size I can have? I cannot have more than this. That is singleton bound. Okay, so this approach is not happy, then I'll tell you another way. So actually, I wrote whatever I done here. If you remove d minus 1 symbol from each code word, still they are distinct as distance is d. But maximum number of vectors with length n is this much. So I just to summarize whatever there. If you not understand this, okay, don't worry. We can read later that part. I'm telling another way. This is for linear code, but if C is a linear code, then what is that we have? Already we know the size, right? Now without, but we want to restrict what is the maximum size, something like that, right? Okay, then cardinality is equal to q power k. But in this case, q power k is less than or equal to q power n minus d plus 1. That is, k is less than or equal to n minus d plus 1. It is equivalently, d is less than or equal to n minus k plus 1, right? This we discussed yesterday. So this is actually continuation to that. In the linear code, what happens? But so look at here. Another way to prove bound is using the generator matrix in the linear code. If the generator matrix is in systematic form, then weight of each row is at most n minus k plus 1. Do you remember yesterday we discussed this?
Yes, sir.
Yeah. Then d is less than or equal to n minus k plus 1, correct? Another way to look at it is that, as you told, Amia told yesterday. But at that I asked only with G, how can you find? But he went beyond. That's why this is the better actually. But even then I'm telling what Amia told yesterday. I wrote to yesterday after he told. Another approach here is to itself, since G is systematic, then k coordinates of all, first k coordinates of all the code words related to fq power k. As the quad contribute distance 1 to those code words, right? So remaining n minus k, so total distance less than or equal to n minus k plus 1. Your idea I put here, but this is little complicated. So this is coming directly with the just the rows of G itself, right? Here we need to go to all the code words, but that much is not required here. But anyhow, so this we discussed yesterday. Do you remember? We have a generator matrix, first I and then systematic form. So you take each row, maximum weight can be n minus k plus 1. Weight of one vector is less than or equal to n minus k plus 1, then distance of the code is less than or equal to n minus k plus 1, right? Yeah. So that is where this definition comes. So finally, the conclusion is that, so once you fix n and d, n and k, if you fix n and k in the linear code, if you fix n and k, then my d is bounded by. So it is giving many ways. You can think of it in many ways. Here it is giving bound for cardinality of C. But here, once you know cardinality of C, it will give bound for D also. Right? Like that, you can think of a single bound. So now definition comes. A minimum distance separable code. A code is said to be maximum distance separable code if the cardinality is equal to exactly q power n minus t plus 1. If so C is a linear code, then D equal to n minus k plus 1. The code which attains singleton bound is MDS code, maximum distance separable code. Okay. So we'll see several examples. Yeah, any doubts related to MDS code? Okay, if there is no doubt, then go. Let us check this example so that it will be helpful to you. So what is this code called? Repetition code, right? Okay. So can you tell me the, you know already, the size is equal to 2, m equal to 2, n is equal to 3, and distance is 3, you are clear with it. And but now singleton bound says that m is less than or equal to 2 power n minus t plus 1, n minus t plus 1. So 2 power, it is exactly 2. So it is equality coming here, 2 equal to 2. So C is MDS code. Okay. Since it is linear, other way to look at D is equal to n minus k plus 1 r naught. So D is equal to 3, n value is 3, so k is 1, right? Why k equal to 1? Yeah, why k is equal to 1? So please respond. You know, but if you know, then it is easy. Why it is a k equal to 1 here? Okay, anyhow. Something you are angry on me, people. That's why you are not responding. Okay, but I'll try to correct it if there is a problem. Okay, k equal to 1 because this 1, 1, 1 vector, it is a linear space of dimension 1. Right? Yeah, okay. So let d equal to 1, right? So look at here. What about this? My C is equal to entire f cube power n, right? Is it a MDS code? Question is this. I'm taking entire f cube power n and subspace, but C equal to the whole space. It is itself is a subspace, right? Now, can you tell me what is n value, k value, d value? Yeah, Amir, go ahead.
N is anyway n.
N only, yeah.
So
K,
M will also
K,
K will also be
N, yeah.
yes,
D equal to?
n minus k plus 1, which is 1.
No, 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 no. No, no, we need to prove that is 1. You are going in a, you are not understanding the problem.
So we have to prove that it is MDS.
Yeah.
Okay, so
No, no, that is okay, MDS or not. See, when I given the code to you, then you can find the distance.
okay, then minimum weight is going to be 1.
Yeah, because
So
I'm
it
taking,
is
for example, n equal to 3, I'm taking all the vectors, right? I'm taking all the vectors, okay? 1, 1, 1. Total 8 vectors are there. If I take all the vectors, it itself is a subspace, so it is a linear code. So in this case, the dimension is same as the k value is the dimension, total n. So, but now, is it satisfies the singleton bound? Since that is it equal to n minus k plus 1? Correct, right? It's happening, so it is an MDS code. Okay. Yes, that is what I want to convey. This is also MDS code, but this is trivial. This is also trivial. These are trivial examples. Okay. One more trivial example is there. Okay. Is it a parity check code? Is a MDS code? You remember what is a parity check code? Do you remember? FQ power k to FQ power n. Do you remember? Parity check means I'm adding all the coordinates, right? Okay, then I'll tell. So this is 1 0 0 1 here, 0 1 0 1 here, right? 0 0 1 1 here. Like that 0 0 0 1 1, right? You know this code, right? So remember that 1 0, we done it actually several times I done, but I luck I'm unable to motivate you to remember this. So we discussed this, okay, in the first class, okay. So this is the sum of all this I'm taking here. This is called parity check code. Okay. Now can you tell me that this is a map from where to where? Okay. So can you tell me k value and n value and all? Now I gave the matrix G. It is a map from where to where. So this is assumed this is n by n. Now can you tell me it is a map from where to where?
FQN
Mm-hmm.
to FQN plus 1.
N plus 1. Okay, just I'm adding. So x1 next to xn map to x1 next to xn and the summation xn. Right, this is the map. This will take care. Okay. So these are clear. So now my n is equal to n plus 1. Correct. Sorry to say like this. If you are confusion, then take k plus 1, plus 1 or something. So here in this case, k equal to n. Correct. What is the distance?
2.
2. You remember this, right? Because now they are all become even weights. Yeah. So distance is equal to 2. Is it an MDS code?
Yes, sir.
Yeah, because you can check the 10 plus 1 minus k plus 1. So it is equal to 2. So
And we saw that the equality occurs only when the last column is 1.
hmm,
Even in the general cases, all the entries in the A matrix are 1, then it is going to be an MDS code.
you are telling that not only here, all are ones, further also.
Yes, sir.
No, I don't know how it is. For example, I add one more, 111, right? It need not be anyhow. So anyhow, we'll discuss that later. But is it MDS code now? Yes, right? So these are very trivial examples. Okay. So here n equal to k plus 1 and d equal to 2, right? So in particular, this example you understood MDS code with parameters n equal to 3, d equal to 2, and k equal to 2. In general, for any k, so code with this generator matrix, whose first k columns are ik. Yeah, it is a, okay. So any questions till now? These problems are okay. We have some examples. Repetition code is an example of MDS code, and entire FQ power n is an MDS code, and this parity check is also MDS code. But these are all trivial codes only. People say these are trivial. Non-trivial MDS codes are yesterday we are discussing Hamming codes. Hamming codes. You remember Hamming codes? Right? Hamming codes are MDS codes. So we'll prove it later, or you can also prove it. Yeah. So, but before going further, you understand some examples and what is MDS code. Now we'll see that more properties of these MDS codes now. Okay. Yeah. So I just take a small break so that it will be beneficial to you. Okay. So yeah, this is the thing. So let the CBA NMD code, NKD MDS code. Okay. Linear code. Then what is that we have d equal to n minus k plus 1 already. Now the goal is that any k columns of G are linearly independent. Okay. So the proof is very simple. We claim that any non-zero code word in C has at most, so this is the goal, but I will prove it. But before that, I have a small goal. We claim that any non-zero code word in C has at most k minus 1 zeros. Right? That is very simple because suppose C has C is a non-zero code word with k or more zeros, then what happens, right? K has more zeros, then weight is less than or equal to n minus k, right? But D is but D is less than or equal to weight of the code, non-zero code word, right? It is a minimum of D is the minimum of all the non-zero weights, right? But n minus k is D minus n, a contradiction. Is it okay? This part is okay. What is that I'm claiming? If in MDS code, number of zeros are at number of zeros are at most k minus 1. Yeah, okay. With this observation in hand, we claim that any k columns in the generator matrix G are linearly independent. How do you prove that? See, we know that first k columns are linearly independent, right? In the systematic form, it is I cross something. So, but it is not telling that you take any k cross k submatrix that is linearly independent. That is the beauty of this. Okay. So, how to prove that part? Let us take G dash is submatrix of size k cross k in the generator matrix K. Okay. That means we are taking the one few columns, k columns, arbitrary k columns, and you generated it. Now, since xg is has at most k minus 1 zeros, so where x belongs to fq power k implies that x dash is not a zero vector. Okay, this is true for every non-zero vector in fq power k, right? That means that x is non-zero, then x into g dash is also non-zero, right? So that means that g dash is invertible. Is it okay or not okay? Not clear?
It's clear.
Yeah, okay. The thing is that what we are doing that I'm taking x into g, but this is it is combination. Some g dash is also there. Okay, x is multiplied to that. Okay, but g dash has k columns, right? So, but we cannot have at most k minus 1 zero. So that helping us that this is g dash is invertible. Okay. Now, if the matrix G, so that entire thing now in this result, if the G generator matrix of MDS code, if and only if every subset of k columns of G is linearly independent by combining both. Okay. Yeah. So next result is that if C, let C be an NKD MDS linear code, then its dual C perp is also MDS code. Okay. So I written some proof here, but I wrote something else also here, maybe which you can take any one of them. For example, if the distance of the code is d equal to n minus k plus 1, that means it is a MDS code. Then n minus k columns of parity check matrix which are linearly independent, right? You understand this? We done it today. See, distance is d, then any d minus 1 columns are linearly independent, right?
Yes, sir.
We observed that if the distance of the code is d, then any d minus 1 columns are linearly independent. So from that, if the distance of the code is n minus k plus 1, then any okay, so I'm sorry, but there is a problem in internet connection. If the distance of the code is n minus k plus 1, okay, the parity check matrix is any n minus k columns are linearly independent, right? Recall the parity check matrix for C is a generator matrix for the C perp, right? So now we can check that we can write H equal to A into H transpose where this matrix is clear. H dash is n minus k cross n minus k. It is clear that H dash is invertible matrix because it is n minus k cross n minus k. Now let us C is in C per has at least n minus k zeros, right? What is that we need to prove? C perp is also, yeah. Can you recall what is that my claim is? We given that C is MDS code. C is MDS code. Our claim is to show that, yeah. Can you recall?
That C perp is also MDS.
C perp is also MDS code. But to prove that one, we know parameters already. This is NKD code. Okay, this is NKD, right? Then we know that. So then C perp is also, there is no change in n, size also n, but here it is n minus k, right? Whose dimension is n minus k, correct? Now what is a d now, right? So in order to become MDS, then it should be, what is a d value, correct? So n minus k plus 1. So this is my n. What is n minus k? N minus k, sorry, n minus k. K is n minus k here and plus 1. So what is happening here? It is k plus 1, correct? So I want to show that distance equal to k plus 1. Distance equal to k plus 1. So that happens only when, so for example, if n minus k or more zeros are there, then what happens, right? Let us check that. So let's see has at least n minus k zeros. Permitting the coordinate does not change the weight of the word. So we may assume that at the last n minus k coordinates of C are 0. The only way to obtain 0 is in the last n minus k coordinates such as C is that this is a 0 linear combination of the rows of H dash by the linear independence of H dash. So that means that we cannot. So what is that I want to say is that let me state here give me 1 minute. So here I wrote something that may make it clear to you. So the goal is to show that minimum distance of the d of C perp is equal to this part k plus 1. We know that we know that d is less than or equal to k plus 1 already, correct? Why it is less than or equal to k plus 1? By that is a singleton bound, right? Hence it is sufficient to show that d is greater than or equal to k plus 1 to become that part. Suppose d is k plus 1. That means every vector in C perp has at least n minus k zeros from this, right? If d is less than k plus 1, yeah, if d is less than k plus 1, right, then so please try to understand this d is related to the C perp d. Yeah, this t is related to C perp d, so there may be a little confusion. Yeah, so every vector in C perp has at least d n minus k zeros. That means, but every vector in C perp has at least n minus k zeros. But G is a generator matrix for C perp. Okay, that gives the contradiction. This is one way because k columns of G are linearly independent. This is one way to look at. Other way to look at is that the here. Okay, so if you once we have n minus k or more zero, then entire code word is 0. That means that so distance cannot be less than k plus 1. That is what goal is. Okay. Yeah. So any doubts or any more clarifications required? There are two ways. One way is directly by using generating matrix. As we already proved that any k columns are linearly independent. That is the first proof. This is a little simpler. Or this is also very interesting. Right? So yeah, you can use any one of them and make it convenient. So conclusion finally is that now you know that C perp is MDS, then C is also MDS because C perp is C. So we have some, these are equivalent conditions actually. What are the equivalent conditions? MDS code if and only if any k columns of G are linearly independent, or any n minus k columns of H are linearly independent, or C perp is MDS code. All these are equivalent conditions. Okay. We'll discuss more about these MDS code future, but this is all about singleton bound. Yeah. Now I'm going to define another bound. This also we discussed a bit. It is called spear packing bound or Hamming bound. Okay. So for that we define the ball, right, with center at t, distance t, right. All vectors with at most distance t from the code word C, right. So that is u belong to Hamming sphere if distance of C comma u less than or equal to t. The number of words in a power n such in such a sphere is called volume of that sphere or ball. VQ, that is denoted as VQNT. Do you remember we done this?
Yes, sir.
We have a sphere or a ball of n-dimensional Q array space, right? The number of elements, that is volume. Number of elements in this is how many vectors which are at a distance 0 from C, that is NC0. How many vectors at a distance 1 from C, Q minus 1. You remember, I hope. Huh? We done this. So Q minus 1 and you choose to Q minus 1 whole square and so on, right? So that means the volume is actually n choose I Q minus 1 power I. Yeah, it is we done in the as a tutorial problem, last tutorial, right? Yeah. Okay, so that is what I wrote here. The proof, I think it is easy for you. We already discussed it earlier. Yeah. Now look at here. Now, so this question also I asked when you distance is you take largest possible distance, then we get all the vectors. That means that this n choose 0 is equal to 2 power n itself, right? Meaning, if the vector v belongs to fq power n, then there is only vector whose distance is 0 from v. I think again I'm explaining that nothing is, yeah. So is it okay to see this fq n 0 equal to 1? Fq and 0 is the volume of the ball with the distance 0, right? Distance is 1, then Vq and 0 means a ball with the distance 0 and this extra vector. Total together is Vq and plus 1. So t value I'm changing, t equal to 0, right? Only this part will come, right? If t equal to 1, both will come. T equal to 2, then all three will come like that. Yeah, this is easy. Okay, now this is the bound. Okay, let C be a Q ray and MD code with the D is greater than or equal to 2t plus 1. Then M is less than or equal to Q power n by NQ NT. Okay, why this is so? What is VQNT? It is volume of the ball with the center at some code word and distance is t, right? Correct. Yeah, it is very simple case. But now I take one code word C. I take one code word C. Okay, C belongs to capital C. Now I'm taking this MCT, right? Then what is the volume of that one? That is VQNT, right? Are you following?
Yes, sir.
I take one code word and around one ball, another code word around one ball, right? Another one code word around one ball. I'm taking with the T, so they will not overlap, right? So like that, each code word I'm putting one ball and collecting the volumes, right? So total volume is how much now? If you collect all of them, that is m times VQNT. Very simple, and not much complicated. Each word key around, each code word key around, I'm constructing a ball with the radius T, right? They will not overlap because the distance is greater than or equal to 2T plus 1. Okay. Now, then it is less than or equal to what? Q power n, because total number of words itself is q power n, right? That is what this bound is. So if we have a, once d is fixed, right? In particular, t can be replaced with d minus 1 by 2. Okay, what is we are saying that this m is less than or equal to q power n by vq of n comma d minus 1 by 2. Okay, once d is given, n is given, then the size cannot be greater than this much. That is what this bound is, having bound. Is okay or not okay?
Yes, sir.
Yeah, Achila, please.
Yes, sir, it is okay.
It is okay because see, what I'm doing, I'm taking one code word C, around which I'm constructing a ball. Now, what is the volume of the ball? Volume of the ball we discussed. This is important. If you want, I can repeat that, but we discussed this. So if you want, then I will do that. Actually, okay. So let us do for one maybe. See, I have a code word C, right? Now this has some positions, right? So C1, C2, and so on, Cn. Now, how many vectors are there which are at a distance 2 from this? For example, I want to figure out. Then what is that I have to choose? First, I have to choose two places among these, right? That is n choose two ways. So once I choose these two places, Manlo, then the C2 and this one should be different, and this should be different. Now, this is already one value. So there are total Q symbols are there. So this has Q minus one choices. This also has Q minus one choices. That is the way we done, right? Now, I am constructing a ball of distance t, means now distance 1, distance 2, distance 3, all of them has to come, right? That is what we are adding. Okay, so now I take one code word and I am constructing a circle around with the distance t. So these are disjoint, but these are contents of code words. Okay, not only code words. Only one code word will be there inside, but remaining are just words, right? So their total volume sum is less than or equal to q power n, because total number of words themselves are q power n. But how many of the circles will come in? There m are there. For each code word, one circle. So m into this equal to this part. Yeah. The proof is simple. Now here, by using here the codes which actually satisfy this, them they are called perfect codes. Yeah, sorry, I may be mistaken earlier. The non-trivial example for singleton bound, I told Hamming codes. We'll check it. Hamming codes satisfy it, but Hamming codes are actually perfect codes. So there is a mistake. Okay. What are these? Perfect codes? A code, NMD code with n d equal to 2t plus 1 is satisfies Hamming bound with equality. It's called perfect code. So what actually perfect code is doing? If I take circles around those code words, then I'm covering entire QN. It is advantage, right? Whatever the received word I get it, then I can correct it now. Okay, I'm not missing any word, right? So let us see one example. Make you help all these things very nicely. Okay, I'll try to help with one example. So those who are not understanding now, they can be clear with that. Okay, so look at here. One example. This we done also in the class, but again I am telling. Mehak, are you there? Hello, Mehak.
Yes, sir.
Yeah, I take your help. Okay, I'm asking simple questions, right?
Hmm.
Can you tell me what is n here?
2.
N means length of the code word, right?
Okay. So it's 5, sir.
5. What is k? K is the dimension of the code. What is the size of the code? That is m. Equal to 2. It is 2 power k. K value is how much?
1.
So I'm facing difficulty. Why still you are confusing with n value, k value? Okay, anyhow, I don't know when you will come do these things. So k equal to 1 and n equal to 5, right? And next, what is the distance?
5.
5, right? Distance of the code is 5 because only 2 words are there and their distance is 5, or otherwise only one non-zero vector is there whose weight is 5. That way also we can say. Okay. Now tell me any vector you like of length 5.
Sir, can you repeat the question?
You give me any vector of length 5 now. Any vector of length 5. Binary vector.
1 0 1 0 1.
Okay. 1 0 1 0 1, right? So now you received this. You received this one. So which code word? These are the code words. Actually, you are sending one of these, but you received this. So you decode it to which code word now?
1 1 1 1.
Why?
Because the distance of 111 and 1010
Is is
is almost same. Means this is 5 and that is 3.
not almost same. This is distance is 2.
Hmm.
Distance between these two is 2. What is the distance between these two? 0 0 0 0 and this one is 3.
3.
The distance is more than this distance, so it is nearer to this, right? So by nearest near decoding, I'll assume that this is the code sent, right? Yeah.
Yes, sir.
You are able to judge, right? This is this one. Yeah. So what is happening? So I take a this. I am. How many circles will come now this time? How many circles will come? Only 2 circles. One is with center 0 0 0. Other is center with 1 1 1 1. Right. What is it? What is it? What is the radius now? So distance is equal to, I write 2t plus 1, or I'll take my radius is d minus 1 by 2, whatever it is, that is t value. So can you tell me what is t now?
2.
This is 2. Now, so you now this vector, so which vectors will be inside this circle? Which vectors will be inside this circle? Yeah. Is it every vector is in this circle or this circle or not? You take any vector. I'm claiming that that will be either here or here. Okay. So their union is equal to all the vectors. Is it clear, Achla?
Yes, sir.
What is it I'm saying? So you take any vector of length 5, okay, then it will be here or here. That much only I'm telling. Because what is the distance, right? I take a vector now, C1, C2, C3, C4, C5. This is my code word, right? Then what is the distance between this and 0 0 0, right? And the distance between 1 1 1. Look at that. Okay. So for example, distance between this and 0 0 0 is 3. Then what is the distance between this and this one is 2, right? then it will be here. Okay, so every vector now it is here or here. If it is not here means what? If it is not here means what? Distance is 3 or more. If the distance from 0, 0, 0 is 3 or more, then it has 3 or more ones. Then automatically distance from 1, 1, 1 becomes 2 or less. Then it is here. Is it tough to understand? So this is a perfect code. Connect, is it clear to you?
Yes, sir.
Right. But now I'm asking another question. So if you are not still clear, so let us look at this. 4 vectors only. Now, again, I'm taking repetition code to make you help to understand. Right. Now, now, what is the distance now? Distance is 4. So what is the circles I have to make now? Circle radius is how much? Again, 2 circles. There are 2 code words. But what is the distance now? It is d minus 1 by 2, right? Greatest integer function. If it is odd, then it is a no problem. No need of greatest integer function. Can you tell me what is the radius I can take? 1 only, right? I cannot take more than 1. Right? So that is the correcting capacity, right? D minus 1 by 2. Only I can correct. Here I can correct only 1. I cannot correct 2 errors happens, right? That you can see. That you can see from the perfect code also. Is it a perfect code, Amiya?
No, sir.
No. Why it is not a perfect code? Can you give one example? Which is not in both of them. Can you give me one vector which is not in both of them?
1010.
1, 0, 1, 0, right? Yeah, good, very good. Yes, you are correct. Why it is not here? Because distance is 1. This is 0, 0, 0, 0, right? Distance between these two is 2. Okay, 1, 1, 1, 1. Now here also the distance is 2. So I cannot have this. Okay. So what is happening? So which vectors we can correct actually? Okay, one error happens, then easily you can correct, right? See, for example, this is I received, then it is inside, then I can correct it to this one only, 0, 0, 0, 0, right? Or 0, 1, 0, 0. I can correct it to 0, 0, 0 only. Only 1, 1 is there, then I will map it to this. This is inside the circle, right? If 3 ones are there, then what happens? Distance from this to 1, 1, 1, 1 is 1 now. So it is inside this circle. So what are inside this circle? Can somebody help me now? What are all inside this circle? All the vectors
With weight 1.
weight 1 or 0, right? What are the vectors inside this?
Again, weight 3 or
4, right? Weight 3 or 4. What about weight 2 and 2? They are nowhere. You see that earlier also I discussed this example. I put like this and I put question mark here, question mark here. You may look at that lecture notes, you will realize. So it is not covering all of them. So their union is not all the vectors. So it is not a perfect code, but this is a perfect code. Now, which repetition codes are perfect codes? Can you now say something?
If n is odd, then it's a perfect one.
If n is odd, then it is a perfect code, right? Right? Yeah. If n is odd, it is a perfect code. So I'm removing all those. Okay, you need to understand. Okay, and assimilate these. So I'm not keeping them. Okay, so I'm not written these notes. Okay. Yeah. So you understand what are perfect codes. Try to find more perfect codes. Okay, but we'll do more and more. So you understand that code should be perfect code. Then only I can at least I can map it to one of them. Okay, now I'll stop with this last bone. This also I introduced this one something AQND. Yeah, what is this? Let alphabet A has two elements given n and d, where d is less than or equal to n. We are looking for the largest m such that NMD code exists. Means given q, n, and d, what is the maximum value of m we can have? That is AQND is equal to maximum of m such that NMD code, there is an NMD code over A. Is it okay? Is A and AQND AQND notation is clear to you? Okay. So actually thing is that, for example, I have some D less than n. Okay, I can construct NMD code. Okay. So I'm not telling it is a linear code and all, right? That's why it is possible to construct NMD code. How? So we can always find at least one NMD code, fix an element B of A. Let's see with a set of all words of the form, vectors of the form A, B, B, B. Okay. Now with the D copies of A, here D copies of A and n minus D copies of B. Okay. With A belong to A. Now there are few such vectors, right? There are few such vectors. Why? There are few such vectors. Once you fix B, we keep change A value, right? Okay, A, B, 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 C, 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 B, 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 like that. Then what can be the distance between them? Is it not clear? So let us example with the ternary code. So ternary code, what are the symbols? 0, 1, 2, right? So I'm saying that I'm fixing one of the symbol. Let us say fix 2. So then I'm saying that D copies of A and n minus D copies of B, right? So my D is equal to, let us say, 5. Okay. And my n is equal to say 4. Sorry, say n is equal to say 10 and 9. Yeah, 9. So then what is that I'm doing? So I'm taking here 0, 0, 0, 0, D copies of A. Yeah, so D copies of A, and this 2 I'm taking 4 times, 5 times, 4 times. Right. Now again I'm taking here 1, 1, 1, 1, 1, 2, 2, 2, 2. Right. And again I'm taking here 2, 2, 2, 2, 2, 2, and again 2, 2, 2, 2. Right. So it is a subset, right? It is subset of a power n. How many vectors are there here? 3 vectors. What is the distance now between these two? What is the distance between these two?
5.
5. Okay. What is the distance between these two?
5.
5. What is the distance between these two?
5.
Again, right? So I can construct a code with these parameters, but at least one code. But what is the size of this code? It is q, right? So n a q n d greater than or equal to q now. That's what my intention is, right? Okay. It is just some example to illustrate what is a q n d, what is the minimum thing, something like that. Okay. For any day, I can construct at least one q. Okay. You already told this in the problem solving session. AQN1 equal to q power n, right? I take all the codes, the distance is 1, and AQNN equal to q. Why this is so? My D now, D equal
We can
to
take the example of repetition code.
repetition code. See, this is the same as that. See, these are now the same I took. Na? This is n minus D, right? Now n minus n, 0. So I am now repeating that these are also zeros. These are all ones. That is a repetition code. So it is always there, and that is in this case we cannot have more than that. That we proved already. Okay, I'm just but again recalling we proved it earlier, right? So this done. This we done already. Yeah. So any questions till now? Are there any questions? You understand this thing? So you understand AQ and D, correct? Okay. Now we need to look at the bounds of this. Even by volume of this n D minus. Okay. The size m is greater than or equal to that. So I will not read. You go through it and let me know. Take some time, go through it and let me know. You understand the proof or not. Is it visible?
Yes.
Means readable means okay. Yeah. Then entire thing will come. Yeah. Just read and I will start discussing on after the end of it. So is it anyone of you followed? So Amya, at least are you okay with this entire thing? Not clear. Okay, so then what you do, you can go through it carefully and we'll start in the next class. It is not complicated. You can understand it's like an algorithm. Okay, we take, there is no, so try to understand, there is no code now as such. We are constructing a code. with at least this many vectors. It is possible to construct with the distance d and the q. That is what we are doing. Okay. So once n is given, d is given, q is also given, then we are trying to construct a code with nqd things. With the size is greater than or equal to q power n by this. That is the goal here. Okay. So for that, what we are doing, we start with one vector. Take any vector. It is now not a code word or anything. Just you took one vector c1, right? Okay, but distance is there. Some distance is given. So you can construct a ball around c1, okay, with the distance d minus 1, which are, now you look at all the vectors which are at a distance d minus 1, right? You know the distance, having distance only, right? Yeah. So you remove all of them. Okay, keep C1 with you and you remove all of them. So C1 also not there and these also not there right now. Now choose, now there are some vectors, now C2 from the remaining. And since all the vectors which are at a distance at most d minus 1 from C1 already removed. Now what is the distance from C2 to C1, right? It is greater than or equal to d. If it is d minus 1, I already removed, right? Now remove all the vectors which are at a distance of at most d minus 1 from both C2 also. Okay. So in the remaining only, na? So they are automatically distance d minus 1 from C, they are already removed. Okay. So now choose C3. Now abhi tak what happened? All the vectors which are removed distance from d minus 1 from C1 as well as from C2. Right. Now you take C3. Now we claim that the C3 to C1 distance is greater than or equal to 3 and C3 to C1 is also distance greater than or equal to 3. Are you okay with that? Right? Continuing in this way, we can choose C4, C5 until we'll get all the no more vectors left. Right? Right? Yeah. So then it is easy to see this part. So a ball, how many vectors it distance d minus 1 contains, right? VQ and D. Okay, suppose after some stage you constructed m vectors, C1, C2. Suppose we chosen C1, C2, Cn. Then we removed at most m into VQ, D, n minus 1 vectors, right? So we can continue all Qn vectors removed, which contains, continue at least this much, right? Therefore, there exists a code C1, C2, Cn with the m satisfying the required inequality. Yeah. Okay, I'll stop here. Go through it again. You can ask in the next class if you have doubts.